Right. How about like geometry? So that'd be great. Trigonometry? Calculus? Group theory? Possibility theory? Don't worry, this should, I hope, be a very understandable talk. Who here has had a computer science class? Okay. Have the talks so far been pretty understandable and fun? Have you guys been to a bunch already? Or do you kind of come and go as you want? Talks. So this is like maybe your third talk today, something like that? Yeah. About right? Have they been pretty understandable, or first, after you get a little while in, is it like your eyes glaze over? Okay. So when I started in graduate school, I thought I intended to get a master's degree in math, even though I'm very much a computer scientist, because I had done a bachelor's degree in math and also done computer science, and I really like math as well. I thought it was really fun and interesting. So I thought, well, while I'm getting my PhD in computer science, why don't I get a master's in math as well? And so the first semester I signed up for a math class just called algebra. Now this was not 7th, 8th grade algebra. This was after you've had a couple of years of abstract algebra. This was like the culmination of it. And after about 2 weeks in that class, I was like, I can either spend 80 hours a week trying to understand this thing that I found very hard and very non-intuitive, or I can focus my time on computer science. So I decided to focus on computer science. But I guess the kind of lesson, or the thing I'm trying to say about this is that it's certainly possible for anybody to go into a math classroom and feel overwhelmed by different topics. Many of the people who I know who are extremely brilliant theoreticians in computer science are not very good in some branches of mathematics, and some who are very good in some branches are not good in others. I happen to have published a couple of papers in a type of computer science, theoretical computer science called graph theory, although I'm not a theoretician. But for me, even calculus was not completely intuitive. I feel some mathematics just kind of resonates, and it just kind of, it seems obvious to me the first time I heard it. So anyway, but a lot of it does not. So one thing I'm going to try to do with this talk is I'm going to give you guys sort of an overview of what it is we're doing. I'm going to ground it in practical examples and ground it in sort of why you want to do this, because I feel like pure math is sort of beautiful by itself, but sometimes it's nice to see what you can use math for, because ultimately math is really a tool. Also, I will try in places to give you the intuition behind what's happening rather than just show you a bunch of formulas with matrices and calculus expressions and then expect you to understand what it is. All right, and so specifically, since I'm a computer scientist, more specifically, I'm a professor who does a lot of work in computer security. Then I'm going to be looking at a technique that we have that uses mathematics to make it hard for people to crack passwords. And this is work that I've done with a PhD student of mine in the computer science and engineering department. So the problem is, and you guys have probably seen a lot of this in the news, where people, all these major companies get hacked, and there's some enormous number of user accounts and passwords that get dumped. Like Adobe had 38 million hacked, LinkedIn had 6.5 million hacked, which, by the way, does anybody have a LinkedIn account here? Okay. Have you had your account for more than 2 years? You have? No? You're all new? Okay. Well, if your parents have one and their account's been around for more than 2 years and their password's not changed, then lots of people have their password, including all my students. We do an assignment where they crack passwords from LinkedIn. So they should really change that. And this is not something isolated to a few companies. There are literally dozens and dozens. We did a study of about 50 companies that have had breaches in the last few years. So it's extremely prevalent. So pretty much anywhere you use, any type of service you use, there's almost certainly been, a password breach for at least some services that you use, I should say. So Gmail, if you use MSN or Hotmail, if you use Yahoo, these have all been broken into and had their passwords stopped. Now, I'm going to talk about how passwords are stored in a little bit, but they're stored using a type of protection called a cryptographic hash. And I'll walk through this in detail so that you understand what this actually is and what this means and how this works. But this turns out not to be a very effective way of protecting passwords. And so I just talked a minute ago about how LinkedIn had 6.5 million passwords cracked, dumped. Hackers were able to crack more than 60% of those passwords. So they were able to crack, around 4 million of those passwords. And the scary thing is that this was 1 week after the passwords were dumped, after the cryptographically secured data was dumped for the passwords. So basically, this shows that the way of storing and protecting passwords is not effective in many cases. And in fact, even like people like me with a laptop, I can sit and crack, in a few hours, I can crack like 30 or 40% of the passwords. So it's very easy to go through and crack, and you guys can too. It's really simple. So let's talk for a minute about how attackers go and crack passwords. So I'm going to talk about how passwords are stored in just a minute, but let's just assume that for the moment there's the way that you go and you crack passwords is that you have to ask, like, is this Joe's password? Is that Joe's password? And so on, over and over and over again. So fundamentally, if you use cryptography to store things correctly, then what happens is that the attacker ends up guessing passwords. So the attacker ends up sitting there trying password after password until finally they find one that works. And so, of course, the best things for them to guess, if they're going to start guessing passwords, they're not going to start with some completely random string of 50 characters. They'll start with passwords like 1, 2, 3, 4, 5, 6, or password, or things like this, because these are passwords that are known to be used by lots and lots of users. Okay. And so there's this measurement of entropy, like how, you can think of this about how random is my password. So the password isn't very random, because it's like a known thing that an attacker is going to guess. And I'm not really going to go into entropy because I don't think it's that interesting to do a deep dive into what does mathematical entropy mean and so on and so forth. But the things I'll tell you is that it's measured in bits, and having more entropy is better. Every bit of entropy doubles the amount of time you would expect it to take an attacker to try to crack or try to guess the passwords. Okay, so let's look at some example passwords here. So we have this password 1, 2, 3, 4, 5, 6. This is probably going to be the first password that somebody who wants to guess your password would guess, right? Because it's the most popular password. At least it was, according to databases that were done last year. A password like Michael was 20th in a certain. These are all from a certain password dump that happened a few years ago. This was the 20th most popular, so this is something that somebody can guess very, very quickly. There's Cassandra, which maybe you would do on the 1,000 guesses in order to start guessing that. There's more rare passwords that are only used by a few people. This is a millionth password in that password dump, and so on. So the larger the number of entropy, the more guesses it has, or the more guesses an attacker would have to do in order to, or would be likely to do to guess the password. Okay, so I hope you guys kind of have an intuition about what's going on here. So you have these two people. There's the server that wants to verify passwords, and the attacker who wants to guess passwords. Okay. Now, if you're designing a scheme that's going to store these passwords, the server needs to be able to verify them relatively quickly. If you go to log into something like Facebook, and it takes you, I don't know, let's say a minute for Facebook to come back and tell you if you typed your password correctly, you're not going to be happy with that, right? You want to be able to try to log into Facebook, and you want to be able to have it come back and tell you something very quickly, like maybe under a second. Okay? So typically the way that it works is the servers that do this verify passwords in 1 to 10 milliseconds. Okay? So that would mean that an attacker who's doing that same effort to try to guess passwords can guess like 100 to 1,000 passwords per second. Right? Does that make sense to everybody? Okay. The attacker that has the same sort of computer as the defender. Right. Okay. And the issue is that people choose really bad passwords. Okay. On average, users choose passwords that have about 20 bits of entropy, and which means that there are many passwords that are much weaker than this. So it takes, even if you just kind of go and brute force every user's password in a naive way, 20 bits, you can easily do this in 20 minutes. If it's 19 bits, you can do it in 10 minutes. If it's 18 bits, you can do it in 5 minutes, right? So as people choose weaker and weaker passwords, it becomes easier to brute force it, and it's hard to get people to remember unique, high randomness passwords per second. Okay, so does everybody get the general problem that we're going after? Okay, so this, right, okay, so the issue is that this limitation is really fundamental, right? Because if the attacker has a computer, has the same computer as the defender, and the attacker has a password database, then if it takes the defender some amount of time to do it, then it's going to take the attacker. The attacker is going to be able to do that. Is going to be able to take that amount of time to have a specific guess. Okay, and if you know things about computer science, and you understand like how computation works, then this just seems like there's no way to get around it, because the attacker has the same thing, and the attacker can do the same thing that the defender is going to do to verify passwords, right? But what I'm going to talk about is a way to use math, a couple of things in mathematics to actually get around this limitation, because it really isn't a fundamental limitation. There's a specific technique that we're going to use here, which is going to make it so that the cost that a defender pays to verify passwords is actually much, much, much less than what an attacker has to try to guess passwords. Okay? And this is for an attacker with the exact same hardware and the password database. All right. And usually when I explain this to a computer science audience at this point, people look very puzzled and they look very upset, like I'm about to tell them something that's like completely crazy. But I'll show you what the observation and the trick is here. So the observation that we make is that when an attacker is trying to guess passwords, they're almost always guessing wrong, right? Because they got this big list of passwords as we saw here, and if your password's Cassandra, which isn't a very strong password, which this can be cracked in like a second, right? Then they're going to guess 999 wrong things before they guess Cassandra. If they do this in an intelligent way. So the attacker almost always guesses wrong. Now, but when people enter their passwords into websites, they almost always provide the password correctly. Right? Overwhelmingly, people type passwords correctly. Okay, so this is the difference. So the attacker gets wrong information, the defender has almost entirely correct information. All right, and so the technique that we're going to have is we're going to check groups of passwords together. We're not going to go and just individually check passwords. We're going to make it so that if you're given a set of passwords, you either know that all of them are right, or at least one is wrong. And you can't tell if any single password is correct in isolation. So just to make sure it's kind of clear like what's happening and how this works. Let's say that, so I asked this question earlier when the room wasn't quite full, but let's say that I don't have any of this information, I just was going to try to guess your years, like who's a freshman, who's a sophomore, who's a junior, who's a senior, right? So if I went around and did that, then on average you would expect that I would make like 2.5 guesses per person, right? If I ask, I'm sorry I don't know your name, but if I asked you, are you a freshman? No? Okay. Are you a sophomore? Okay. So in that case I got slightly lucky. It took me 2 guesses to figure hers out. If I say, are you a freshman? Are you a sophomore? Okay, I got slightly lucky again, 2 guesses. So you can see that for each person I'm asking, it's going to take me, up to, in this case, there's 4 possible guesses I'll have to make. So it would take me up to 4 times per person to go and make, and to guess. Now, given that we have, I don't know, about 20 people in the room, then within 80 guesses, I for sure could know everybody's year, right? Now, a different way of doing this is if you're required to do the guesses together. If I have to say, are you a freshman, are you a freshman, are you a freshman, are you a freshman to everybody, and you guys all huddle together and whisper, and then all you tell me is yes or no, then I have to do many, many more guesses, okay? And the reason why is because effectively what's happening is I have to be right with every single person, okay? In order for me to get a yes answer out. So the way that this works is instead of it being before it was there's k guesses and there's n people. So before it took me k times n in order to go and guess everybody's year, all right? But now what it's going to take me is k to the nth power to guess all of your. If I have to guess them all together, and you just tell me yes or no, I have many, more things I can guess. And this is actually a principle that comes in a lot of places in passwords and security and things like this. So one of the things I teach in my introductory security class is I teach you how to open combination blocks if you've forgotten the combination key. Okay. And the basic technique that you do to do this is, depending on how the lock is manufactured, you can usually figure out the correct numbers for each dial individually, right? And that has exactly the same property where you're only making a small number of guesses. You're making k guesses per dial of a combination lock, right? And then, as opposed to having to make k to the n, to guess k to the n combinations, right? Do you guys understand this? You guys get what I'm getting at? Okay, good. Don't hesitate to stop me. I can give other analogies and things if I go too fast. All right. So the way that this works is, so this is basically what I was just saying. So cracking k passwords, where if you have a server check time of v, then what happens is that you would just go through and try them individually here, and the cracking time is approximately n times k times whatever the verification time is, right? And then what I was saying is that if you have to guess groups of them together, like in this case we have to guess 3 of them right before we know if any of our guesses were correct, then the verification time becomes n to the k. And this is an enormously larger number than this is, right? Does that make sense to everybody? Okay. All right, okay. So that's the basic trick. That's the basic idea. You guys have the mathematical or you have the intuition behind what's happening in this. So now let me explain some more background about how this works and try to give you some intuition about how we actually make you check sets and how this works and what happens. Right. So first of all, the way password storage works in general is there are these things called secure hash functions. Sometimes they're called cryptographically secure hash functions, but they have names like SHA-1 or to some extent MD5, which is a little flawed. But they have names like SHA-1, SHA-256, things like this. And this is a one-way function. So it has this property where it's believed it's very hard to, that if you're given the output of a function, so if you know that f of x is equal to y, and you know f, and you know y, it's impractical to find an x that produces y. Okay, so that's the basic idea. Okay, and there's slight. I'm glossing over a few things, so but this is the thing you need to understand for what I'm talking about here. There's much finer grained definitions and ways of talking about this, but this is kind of good enough to think about. So, given the output and the function, you can't. It's infeasible for you to really find an input other than doing things like brute force guessing every possible input until you find one that happens to match it. Okay, so what happens is when people want to store passwords today, they take some password and they put it through these functions, and out comes something that looks like this. Okay, this is the output. This is a fixed length thing that represents the hash of the input. Okay, and every time you put password into this hashing function, if password is the string, then you will always get the same output. If you put in 1, 2, 3, 4, 5, 6, then you'll get a different output. Okay, and and the reason why you want to have a function that does this, so this is effectively kind of scrambling the input, right? So that somebody who steals this information, all they see are these hashes. The reason you do this is because if somebody steals this password database, what you don't want to have happen is you don't want them to just get a plain text list of everybody's password. Because then they know all the passwords and they can break into other websites and do all kinds of illegal things with those. Okay, because people reuse passwords across websites, am I right? Okay, all right. Which, just a momentary aside, LastPass and 1Password are both very good sites that will make it so you don't have to do that and you only have to remember 1Password. So there's good password memorization software out there if you want to be more secure, which I recommend you do. Okay, so this hashing function lets you avoid storing raw passwords. Now, there's a weakness if you just take a password like password that produces that hash and stick it into a database. Now, does anybody spot the weakness? Yes?
Break into the database and get the hashes.
But yeah, you break into the database and you get the hashes, but if password hashes to this value, then you just know that that value is always password. So whenever you steal a password database, you can just look through it for the hashes of common passwords, and you don't have to check anything. You just know. You can create what's called a rainbow table, where you can build a dictionary of the hashes of common passwords. Okay. So what you could do is then just look things up. So what happens is that in order to prevent this, people put a random value in to the hashing function along with the password, so that even if like, let's say you and I both have the same password on the same site, the hashes won't be the same, right? Because I guess that's the other problem, is that if 50 users all chose the password, you'd have 50 entries that all have the same hash. And that would be a pretty good hint that that's a really bad password. You might not know exactly what password it is, but you know this is a really bad password because so many users have chosen it, right? So what you do is you have a random salt value that's used per account. Every account has their own salt. It's just stored in plain text in the database. And what this does is it makes these databases of passwords impractical. Because if you have something like 32 bits of random salt, then well, what does that mean? How would that make it harder to build one of these tables? Your table would have to be 2 to the 32nd power larger, which means that if you only wanted to have a table that just stored the hash for this one value, this one really, really weak password, you would now need to have 2 to the 32nd power entries, which is about 4 billion entries, just to store all the hashes of 1, 2, 3, 4, 5, 6. So you can see that you can't really build an extremely large table for that. And many things we use, like 64 bits worth of salt, which makes it completely impractical to even think about trying to build one of those. Okay. All right. So now let's look at kind of how this works. So I'm going to walk through this just to be sure it's clear to everybody. So what happens is that, let's say Joe here wants to log in, and this is how password storage works today. So what Joe does is Joe types his username and his password, which is let me in, which is not a very good password, but that's okay. It gets encrypted and sent to the server. The server gets the password and the username, Joe let me in. The server will go through and find Joe's entry here in the password database. Here we have the salt, and here we have the hash. Okay. The server takes Joe's password and the salt, right? And it takes these two values and it hashes them. That's the H there. And it gets a value out for this, a hash value out. It checks to see if these two match. And if they match, then Joe entered the correct password. Okay. Does that make sense to everybody? Okay, great. All right. Now, in order to make all this work, remember for our scheme, we want to be able to check passwords in sets. We want to be able to check groups of passwords together. Okay. So what we're going to do is we're going to use something called Shamir secret sharing. And I'm not going to explain this in an immense amount of technical detail, but I'll give you the intuition behind it. So the idea is that you have something that you split into shares. Each individual share can't be used to recover the secret, which could be a key, it could be whatever, it could just be a random string. If enough shares are combined together, then you can recover a secret. So the way to think about this is, if you've ever heard this thing where on the submarines, the nuclear submarines, the two people have to turn the keys at the same time, and they have to have the right key. There's two people have to come together to perform some action in order to make the system work. And Shamir secret sharing is a very similar thing where you go and you split a secret into a bunch of shares, and if you have less than a certain number of these shares, you can't learn anything about the secret. Okay? If you have more than that number, then you know about then you can recover the secret. So let's look at how this works. So in the beginning, let's say that we took the secret and we split it into 4 shares. Let's say that the way that we did this, we made it so that you have to have 2 of the shares to recover the secret. So what happens here is somebody who only has 1 share, they actually don't learn anything about the secret. They cannot recover any information about it. The only thing, they don't know. It's not like they get like part of the message or whatever else. They don't get any information about it. If they have at least 2, then they can recover it. And they don't have to have the first and the second. They could have the 4th and the first. They could have any of these 2 and be able to do it. Okay. And if they have more, that's great, but they're not necessarily needed. So as long as they at least have 2, then they can recover the secret. All right. And then here's the scary math behind it that uses a lot of that requires you to understand a bunch of stuff about polynomials and group theory and stuff like that. So I'm not going to talk about that, but what I'm going to do is I'm going to give you the intuition behind it using something that's more understandable. So if you have like a two-dimensional space here, right? Imagine that the secret that you have is a line in this space. Okay, it's maybe something like the slope of a line. Right? Does that everybody understand what I'm talking about? Okay. So now, let's say that each of the shares are a point in the space, right? So if I give you 1 point, then what is the slope of the line? What do you know about the slope? Nothing. If I give you 2 points, oops, well, that's not very, there we go. Good thing I'm not an art professor. If I give you 2 points, right, if these are the secrets, right, then if you have any 2 of these, then you can reconstruct the line and figure out the slope. Does that make sense? And now, if I wanted to do this where I wanted to make 3 things have to reconstruct it, then what I could do is I could make this 3-dimensional space, and I could make it be a plane instead of a line, right? So that's kind of the intuition behind ways in which you can do this. Okay, does everybody get the concept here? Great. Okay. And then one more thing. So, who's seen exclusive OR before? XOR. Okay. So this is an operator like a plus or minus, things like this. You can think of it in the same way. Only it works in a different manner. So what happens is that usually for something like addition or subtraction, you understand, everybody understands from first grade or whatever what the rules are about what you do with the digits. Exclusive OR is very simple. So what you do is if you look at these 2 digits, the first 2 digits, and if these digits are the same, then the result is a 0. If they're different, then the result is a 1. So here, since 0 and 1 are different, I guess I started the other side. Sorry. Since 1 and 1 are the same, then this is a 0. Right? Since 0 and 1 are different, then that's a 1. 1 and 0 are different, that's a 1. 1 and 1 are the same, that's a 0. 0 and 0 are the same, that's a 0. Right? And 0 and 1 are the same, that's a 1. Okay, does everybody see how that works? Okay. Now the reason why this is interesting, and by the way, this is used a ton in computer science. This is like one of the, this is one of the things that comes up over and over and over again, is it has this really interesting property here, where let's say you have A, and this is the symbol for exclusive OR, A XOR B is C. Then what this means is that C XOR A is equal to B, and C XOR B is equal to A. In other words, if I just write A, B, and C, you can put the XOR anywhere you want and the equals anywhere you want. You can reorder them any way you want, and what you'll end up with will be correct. Okay, it'll all be equal. So put the equals anywhere you want, order these any way you want, put the XOR, and this will all be the same. And also, if you XOR all of these together, then you'll get 0. It's another property you have. Okay, if you do, because A XOR A is equal to 0. So if you think about, okay, because remember, think about what happens here. If the things are the same, the result is 0. So all the bits of A are equal to all the bits of A. So therefore, A XOR A is going to be 0. Right? So it has this nice property that it kind of like you can cancel it out. You can recover things from it. But also, yeah, okay. I'll use that. Right? Does this make sense to people? You guys get the gist? Half an hour. All right. So now I'm going to talk about how we use these things that I've discussed. So basically, everybody today, the state of the art that most people use is salted hashing. which is the salting and the hashing that we saw. And I'm going to show you how we use the Shamir secret sharing and the XOR to do this verification of sets. All right. So the way that we're doing this is, once again, you use the password. So Joe's going to provide a password, but instead of going and just checking to see if the hash is the same, now we're going to check to see, effectively, does the point lie on the line here, right? Because that's what means it's a valid share. If the point is on the same line as all the other points, then we know it's a valid share, right? So does that make sense to people? Okay. So everybody's password is a point, and if I have these passwords already, all on this line, and you give me your password and your password's on this line, then you almost certainly, with extremely high probability, give me the correct password. Okay, so Joe enters his password, let me in, just like before. It gets encrypted and sent to the server. The server gets Joe and let me in. The server goes and finds Joe's entry. It hashes Joe's password and the salt, just like before. But now, if you remember, this was the hash of that. But here we're not storing the hash. What we store instead is we store the hash. So we're not doing that comparison. What we're doing instead is we're going to take. It's not what I was hoping I was going to show. So we're going to take groups of other passwords together at the same time, and then use them to recover the shares here, and then check to make sure that this all is correct. I think I'm missing a slide. I apologize for this. So let me walk through and show you how this works in a little bit more detail. Because what happens is that we, in the password database, we store the share, and we store the salted hash of the password, but we XOR them together, right? So when you get one of them, like let's say you get the salted password hash, then you can do the XOR operation. What happens if, right, so, sorry, this is Bob. So let's say I have this value from Bob, right? And somebody enters this password with the salt, I can recover this information. So I take this, and I XOR it with this, then what do I get? I can get the share back, because this is effectively, right? So we have the share, which I'll call S, XORed with the hash, right? Okay? And then we have the data in the database, right? So if we're the server doing verification, then what do we get? We get given the hash, and we know the database, right? So if we XOR these together, then what do we get?
Sure.
The share, right? So then when we get the share, then if we have enough of these shares, we can figure out that they all lie on the same line, right? Does that make sense? Okay. See if there's anything I really want to say here. I think we've already kind of said this. Okay. So the way this can work is, in the beginning, when the system restarts, you can just sit around and wait for at least k people to log in, where k is the number of shares that you need to have to recover this line. Okay? So in my two-dimensional case here, it was 2. In three-dimensional case, it would be 3, so on. So after k people log in, then what I can do is I can recover their shares, and then I can try to see, do all of these points lie on the same line? Right? Do these make sense? And if this is correct, then I can go and validate. I can go and validate the future accounts, and I'll show you how that works in a minute. Let me show that here. So when Bob goes through and enters his password, then what we do is we take we find the salt and we find the share number. We are able to calculate what the share is supposed to be, and then we can check that this property is true. Does the share that we recover XORed with the hash that they provided match the entry here in the database? And if this is true, then we know that they've provided the correct password. Okay? Adding an account to a database is relatively simple. So you just find a share that's unused. So you find, so in this notion of this line here, you find, let's say, an X value that hasn't been used yet, right? You generate a random salt, and you store the user, the share number, the salt, and the hash of the salted password with this point in the database. All right. So, who's a little lost right now? Who's totally tracking and like I can sit down and just give the rest of the lecture? How about that? That's an easy question. Okay. Let me just to make sure, because I want you guys to. I'd rather have you come away with a little bit of information than go over a lot of stuff and not have you guys get it all. And I know you guys do most of it. So, back up a minute here. All right. So, the way our scheme works is usually this stores just the salted hash in the database. Okay. So what we're doing is instead of that, we're storing the salted hash XORed with the share, the point, at a specific location. Okay. And you can view this as we put every point, every share has a number. You can view this as something like the X coordinate of it. Okay. So if I just tell you, so for instance, if you know that in the password database, if I tell you that there's a line and the line has points that have X value 1, 2, 3, 4, and 5, that doesn't tell you anything about the slope of the line either, right? You just know that there's some point somewhere that has some X values. You need the X and the Y to be able to recover what's interesting about it, okay? So you can think of it as being that way. So what is actually stored in the database is the share itself, which in our example would be, the Y value, and it's XORed with the salted password hash, right? Now the reason why we do that is because if you just have the password database and you don't know what this value or this value are, then this is just something that's this is effectively mixed together. So maybe I can explain it this way better. So if you don't know a threshold of shares, right, then you can't get the salted hashes out because you don't know enough shares to recover the secret. If you know enough of the shares, then you can recover the secrets. You can recover any salted hashes you want to verify any passwords. Okay? So it has this protection property that basically the way to think about it is that if you know a threshold of passwords, then so if you know enough points here, you can reconstruct any point on the line, right? And since each point hides a password, then knowing enough points lets you recover any of the password hashes in the database. Okay. All right. Does that kind of make sense? Yes.
In practice, what would be the threshold value for database?
Usually, so I have some at the end, but usually it would be about 3 to 7. So it doesn't have to be a particularly large number. In part because this doesn't have to be that large before you start to see an enormous benefit from it. Exponentiation is really powerful. All right. I think maybe I'll talk. No, I won't go through this. All right. So let's look at like how this works and why this works, and to see kind of what effort the server is going to have to do to validate logins, and versus the attacker having to do to crack passwords. Okay. So for a server, they get almost all legitimate logins, like about 96% in practice. So if this is a probability, then the probability is very high that the passwords they have are correct. The attacker is overwhelmingly going to guess wrong, because even if they guess the most popular password, it's used by less than 1% of users for most of the password dumps, the password databases that didn't use salted hashing that were dumped showed that. So the probability of an attacker having any individual guess be correct is very low. All right. So if we look at this, what this graph shows is this is sort of effort in number of operations, and I didn't put an axis on here, but you can just imagine that this is like seconds, just to make this easier to think about what's happening. And this is the probability of a specific guess being correct. Okay? So the server guesses are going to be over here. So, this is on the order of 10 seconds, right at the top of where my finger is. And these values are much higher, as I'll show you in a sec. So the attacker is doing work over here, and the server is doing work over here. Now, and one of the things I want to point out is this is a logarithmic scale. Okay, so that means that every little bit of separation here actually is a huge value, is a huge difference. Okay, so we have 100, 10,000, a million, right? So this is going up just this much is an enormous jump. Okay, so let's say you have a threshold of 4, which is a pretty simple number. This, to do verification, if you're a server and you're in this place here, takes you like a little bit under 3 seconds to verify those passwords. That's your expected amount of work that you'll need to do. Whereas the attacker, if they're going to guess, it's going to take them about 10 years to guess 3 passwords correctly. And that's if they go through and they just try to do like 1, 2, 3, 4, 5, 6, the most common password, and try to guess that for groups of accounts. It will take them that long to go through and be able to correct 4 accounts that all have the weakest possible password in them. Okay, because the problem blows up combinatorially. It's exponential. It's a huge number. Okay. Right. So I think this is a good point for me to pause. Like, what question? Does this make sense? Yes.
It makes sense as you're feeling about it. If you were logged into your website and your request got approved, a bunch of other requests, would the server have to send out a message saying one of you editing the correct password?
What it would likely do is before, okay, so there's a bunch of practical things to talk about. What it would very likely do is it would very likely, so there's 2 ways of getting around this. One way is that what you probably do is you see a message that the system is booting up. It will take a few moments to process your login, and it'll sit there and wait. It won't tell you anything because it's not going to know individually for your login. Is your login correct or not? Okay. One other thing I didn't really mention, which I probably should emphasize a little more, is that once you know, like let's say there's K passwords. So let's say that you know 3, the K is 4, and let's say that you got your 4 correct passwords. Now any other user that comes along, you can check them very, very quickly. Because even if you think about right, so basically the way you can do this is you already know the share, okay, and you know the stored data, and they're going to give you their password, so you just hash their password, an XOR and check. So that operation is not something that takes like 3 seconds to do. It's something that takes like well, I have some performance numbers, but it takes less than milliseconds to do. You can do thousands, tens of thousands of them a second, even on like a laptop like mine. So it's very, very fast. So this is actually, the other kind of interesting thing is that this cost is something that the legitimate server only pays one time after they reboot. They pay it once after they reboot, and then they don't have to pay this again because they just have to recover the share once. Whereas effectively what's happening is that the attacker, every time they make a guess, they continuously have to pay a lot of effort. Okay, so you had a nice question. I'll get to that in a second. Let me mention a couple of other things first. So you may have sites where any users can create accounts. This could be a problem. We have a mechanism to get around this. I guess I won't talk about this too long. Right. So you have this nice question about what do you do after reboot? How do users log in? There's another way to get around this, which is you store some portion of the hash to do like a probabilistic verification on reboot. So what you would do is you might be comfortable with something like Facebook, where maybe you're not the most concerned person in the world if somebody gets in your Facebook account, obviously depends on what you document on Facebook. But if Facebook says we're comfortable with like a 1 in a billion chance that somebody types a wrong password and they're able to be let in, as long as our users don't see any delay, then what you can do is you can store some correct bits of the password, and then as soon as the system restarts, you can validate using only those bits, right? And this will actually weaken the passwords from the standpoint of the way that the attacker cracks them, which I'm not going to go into detail because it's too complicated for this talk slide. But it weakens the security of the stored passwords by a moderately substantial amount. So you want to be a little careful with this. If they're very, very weak passwords, like 1, 2, 3, 4, 5, 6, or something like this effectively gives them away. So this is better used on sites that have those kinds of rules that you see, where it says you have to, your password has to be 8 characters, and it has to have a lowercase and an uppercase, and it has to have a number and a symbol, and it can't be password with the P capitalized and the O as a 0 and stuff like that. Okay, so, right, and then I won't talk about those. All right, so since I'm very much, practitioner, I want to look at how do we use math to solve real-world problems. What can we do with it? I'm going to talk a little bit about, does this actually work in practice, and can real systems be built using this, and can this actually happen? Does this perform well? Okay, so I wrote a Python implementation of this. It was fairly simple. It was 137 lines of code, and I added these other things, some of which I talked in, some I didn't. About 50 lines of code. I wrote some libraries to do GF256 machine reader sequence sharing. So this took me, I think, about a day and a half to do. It was really straightforward. I've had other people go and build implementations. My student Santiago built an implementation in C, and he worked with an external developer who I don't have his permission, and since this talk is being recorded, I didn't get permission from other people who have contributed things like this to say their names publicly. But I guess you can probably figure it out from our GitHub page. So there are other implementations available in Django. A different developer wrote one in Ruby, there's one in PHP, one in Java, which I need to list here, but I forgot to add. I have a high school student, Emily, who's coming to build a JavaScript implementation in my lab over the summer. This is actually relatively, I think it's a fun, cool thing to kind of work on and do things with. I also have an undergraduate from India, from one of the IITs, she's coming to do some more kind of mathematical analysis behind this to see if we can get better exponential properties out by using ways of reconstruction other than Shamir secret sharing. And this is actually something that we've rolled out on a couple of servers at NYU that run something called the Seattle Project. It works fine. We haven't had any complaints from the people managing the servers. They seem to like it. And we're working with folks at National Geographic. You guys know National Geographic? Okay. So they have an online magazine that they're interested. The developer from there helped us with the Django implementation. They're interested in deploying it. We have several other groups who we're in discussions with that we hope to have this rolled out in within the next year or so. Okay, so a couple natural questions you might have is this reasonably fast? Okay, so, and for what is fast? So remember the threshold values that we're likely to use are probably like 3 to 7, so they're in kind of this range. So really, I'm just showing you this part of the axis just for kind of completeness, right? But we don't actually anticipate people are going to use things over here. Right? This is 1 millisecond. So this is operation you could do in under a second. And here, I don't use any techniques that... so this is showing you the fastest way to do it securely. In practice, you might use techniques that make it intentionally take longer so that it is harder for an attacker to try to crack things. Remember I said I had that axis where I showed effort and I didn't label it as seconds, but I said you can think of this as seconds, right? So there's things you can do to artificially move these up as high as you want to move on here. Okay? These are microseconds, so this is, you can do, right, okay. So the common operation, so the unlock, this is the operation that has to be done once per week. This is the black circles, okay? So for threshold values that are expected, this takes under a millisecond to do if you wanted to do it quickly. You can, once again, you can make it as slow as you want, but the fastest you can do it is under a millisecond. For normal account creation and verification, they're all down here. So you can do tens of thousands of these per second. Right? So it's extremely fast. By the way, these are all numbers off of my laptop, which is not a traditional, server class machine that you would have at a major institute or at a major company or something. So the performance is good enough. Sorry, yes?
Why is that when you increase the threshold value, it takes longer?
Okay, so the threshold, remember here we have a threshold of 2, because we're in a 2-dimensional space, right? So if you have to compute a plane in 3-dimensional space, that actually is more expensive than computing a line in 2-dimensional space, okay? And if you go into 4-dimensional space and you have to compute a hyperplane, that becomes more costly. So the cost goes up because of that. Now, the cost really only goes up for a couple the noticeable increase is really for unlocking. This is really the only thing that makes any substantial difference. Okay, the rest of these, I don't think this increase really matters a lot. And once again, the part of the graph you're probably at is you probably aren't going any higher than, even 16 I think is really pushing. Like 8 is probably as high as you would ever need to go. Yes? Of course, of course. Okay, it doesn't use much additional disk space. I won't get into much detail about it. It doesn't use much memory disk space, so that's not really a problem. Now, let's look for a moment at what happens if people choose actually reasonably good passwords, like random passwords with this. And I've worked at companies and I've had jobs where our passwords were not things we could choose. They were chosen for us. They were generated randomly, and you had to know this was your password. You had to memorize it. So what I'm going to show here, what this graph shows, is it shows how long it would take to guess if the attacker can do 1 billion guesses per second, which is what they can do on a laptop with a GPU. And I'm going to show you different ways of storage, like with our system. So this is the state of the art today. So if you had a like 6-character random password, and somebody can crack this in like 20 minutes, I think this is what this point is. Okay, so it's very fast. Even if you have a very small threshold of 2, right, which is much smaller than we would recommend people use. If you have, and if people use 6-character random password with a threshold of 2, it's going to take millions of years for an attacker to crack this, right? Extremely, extreme difference, 20 minutes to millions of years. Now, you might notice that I'm missing something on here. I'm missing this kind of k equals 3. I'm missing this threshold of 3 value here for random passwords. The reason why is it doesn't fit on the axis, right? If I wanted to go and put it, I'd have to remove the ceiling in order to make, to put the point on the graph. And just to give you an idea about how if you have even 6-character random passwords are considered to be very weak, by the way. You're not supposed to use them in most, organizations. They're considered to be too weak. So almost everyone uses 8-character random passwords if they use random passwords. Okay? So if you use 6-character random passwords and you set a threshold of 3, I just want to compare this. So this will take 1.25 times 10 to the 19 CPU years, right? Which, I mean, sounds like a big number, right? But how big is it really, right? I mean, how do you compare this to other numbers? Well, I have a nice kind of way to compare this that I think makes this more real. So suppose that you took every computer, there's about 900 million computers on the planet, and they had existed and been trying to crack these passwords for the time of the age of the universe. So from the Big Bang until now, they have been continuously running. Every computer had existed and had been running. Then they still wouldn't have gone through and had enough CPU years to catch up with this. Right? So a threshold of 3, 6-character random passwords, every computer that exists today working from the Big Bang until now would not have had enough computation time to crack it. Okay? So it's a very, very big number. Okay, so to conclude, this is a really simple way to protect passwords. We use the secure hash function, special crypto system. It's software changes on the server. It often makes password cracking impractical. And here's a link, which I think we'll just link to our GitHub. In case you're interested and you want to learn more about it. Yeah, with that, I'm happy to take any questions with anybody left. Yes?
Can you go over a little bit about the XOR?
Sure. Okay. So here's a way of thinking about it. Okay. Right. So basically, if the bits are the same, then the value is going to be a 0. So one way of thinking about it is to think of it as something like addition, where if it overflows, you don't carry. Okay. So 1 plus 1, right? If this is base, this is base 2. So 1 plus 1 in base 2 is going to be, it would be like 1, 0, right? But if you throw away the carry bit for every operation, then 1 plus 1 is 0, right? 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0. 0 plus 0 is 0. 0 plus 1 is 1. And like I said, it has this nice property that really you can take and you can reorder these in any order, and this will be true. You put the equal sign anywhere and the XOR operation anywhere, and it will be true. Okay. Does that help? Yes, sir.
So when you have like an original password, the hash changes it into like what the database has, right? So then the salt changes that too.
Yeah, you can. Yes, the salt changes the results of the hashing function. You can think of it as just the salt just being a random value that you just stick on the front or the back of the password. That's a perfectly fine way to think about it. Okay. And the point is that it adds randomness to the passwords, but it's randomness that the attacker can, will know what it is when they still pass the database, because the salts are all there. Okay. Any other questions? Anybody else? Yes.
You know, like about like when will this actually be
In all of these settings, I don't know. I hope soon, but no. I mean, I've done work that's been deployed by companies and organizations. I try to do a lot of. I really make that a focus of what I try to do, and I have learned that predicting when things will get adopted is, really hard to do. Sometimes things that don't seem like they would be that aren't easy for people to adopt and require no changes. Sometimes they take a long time. Sometimes things that are, major changes, all of a sudden the community gets excited and they dive in and they start to alter things. So we'll see. Yes, last question.
So if you put a salt on a password, a rainbow table will be like useless in any case.
No, so rainbow table isn't always useless when you have a salt. If the salt is long enough, so effectively every time you increase the length of the salt by 1 bit, you double the amount of space you need to store. You double the size of rainbow tables that the rainbow table would need to be. So if you make the salt be something like 1 bit, then that doesn't really help you much. Okay? If you make the salt 64 bits, then all of a sudden there's no way that anybody's going to build a rainbow table. Okay, thanks. Had a great time.
Thanks for the lecture.
Thank you.